This lesson, we're going to talk about exponential growth and decay model. So this is the basic form of exponential growth and decay. When we're looking at example 1, it gives you similar form. And this is for bacteria growth functions, which is the exponential model, right? You have exponent with t on the exponent. N is measured in gram, and T is measured in day. T is times. E is the Euler's value, as you see. The first thing they're asking to find the initial amount of bacteria. So if this is going to be the exponential functions, then we can let t equals to 0 to find the initial amount. So let me write that down. A. Initial amount is going to be when t is equals to 0. So when we replace that, 100 times e to the 0.045 times 0. So that's going to have 0 exponents. Any number times 0 will be 0. Any number to the 0 exponents, that's equals to 1, which is going to give you 100. So that's the initial amount, right? 100 grams. Let's look at the B. B is asking what is the growth rate of the bacteria. So when you're looking at your formula or exponential function, your rate is going to be this, which is 0.045. When you convert that into percent, it will give you 4.5%. That's your rate. C, they wanted to know what is the population after 5 days. So all you need to do is just replacing t equals to 5. Then if you plug in those numbers in the calculator, it will be something close to 125.2 grams. So within 5 days, about 25.2 grams grows. Let's see, what about if we're looking at D? D is asking how long will it take for populations to reach 104 grams. So we wanted to know the times. So this is going to become 104 when you started from 100, right? And your rate is 0.045, and this time you're trying to solve for t. First thing you wanted to do is dividing both sides by 100 to isolate exponent by itself on the one side. So this is just going to be exponent, and that's going to be 1.04. Once by itself, exponential by itself, now you can multiply natural logarithm functions. Why do we do that? So we can bring down our exponents into the base using the property of logarithm. So this becomes 0.045 t to the ln e, where we know ln e is equals to 1 because it's log e to e, right? And this is going to be ln 1.04. In order to isolate t by itself, you're going to divide both sides by 0.045. So where your t is going to be somewhere close to, so let's round it, 7.5 days. let's do one more. E, what is the doubling time for the populations? So when you double starting population, which is the initial populations, being 100, that's going to make it 200. So in order to make 100 to 200, how long, right? That's what it's saying. So again, we're looking for t. So we start by dividing both sides by 100. So we get 2 equal e to the 0.045t. Let's multiply both sides by natural logarithm. So we can bring our exponent down. And we know that's going to be 1. So in order to solve for t, now we divide both sides by 0.045 again. So that will give you t equals to natural logarithm of 2 over 0.045. That will be 15.4 days. Okay, so if we're looking at example 2, this time they're asking, so this graph shows that U.S. populations in millions. They're selecting 5 years from 1970 through 2007, 1970 through 2007. And 1970, it started with 203.3 millions, and all the way to 2007, 300.5 millions. With this information, they want you to find the exponential growth functions. It is growing, so it's a growth functions, right? So let's see how we're going to do that. Remember the format of the functions, right? So you have a equals to a sub 0 times e to the kt exponent. So of course we wanted to know the t because we wanted to find, so in the beginning we wanted to find the rate, this k. In order to do that, t, so we need to find the t. T is going to be from 1970 through 2007. So when you subtract that, it will be 37 years. And again, k is what we're looking for to create a exponential model functions, right? And then what will be a? A will be starting, a sub 0 will be the starting populations. And then a will be the final populations in that graph. So when you replace that into the function, you will end up getting 300.9 equals to 203.3 e to the 37 to the x exponent, or let's say x or k, whatever that value is. That's going to be rate, right? So we will divide both sides by 203.3 to isolate exponentials on one side, and we will multiply by natural logarithm to bring down the exponents. And when we do that same thing on the other side, multiply by natural logarithm, know ln e is equals to 1. So then we will divide whole thing by 37 also to isolate x. So your x become this, right? And when you replace that into the calculator, you should get something close to 0.011. So that's going to be your rate. So if you wanted to find the exponential functions, this is going to be starting populations times e to the 0.011 t will be your exponential functions. So with that, this given charts or graph, we should be able to create the function. Once we have a function, then we should be able to answer the second part. So they wanted to know which year the population will reach 315. So this amount, total amount, become 315, and what will be t. So when we do that, we're going to start by dividing by 203.3 on both sides. So it will be only exponent. And then multiply to bring down the exponent. And when you multiply the other side by exponent also, this is what you have. And we know that ln e is equals to 1, so when we divide the whole thing, or both sides of equation by 0.011, that will give you how long, right? So this is going to give you something close to 40. That means 40 years after 1970, the starting year, right? So when you do 1970 plus 40, it will be somewhere around 2010. So year 2010, your population will reach 315 million in that problem. Okay, we're going to try one more time. This time, we're going to look at the decay model. So it said that use the fact that after 5,715 years, a given amount of carbon-14 will have decayed a half of original amounts to find the exponential decay model for carbon-14. So using this information, you're going to find the function. Once you found the functions, there is part 2. So they found that sea scroll, and that contains 76% of the original carbon-14, and it was found in 1947. And we wanted to estimate the age of the Dead Sea Scroll. So first thing first, let's try to find the function first. So after 5,715 is going to be your t, right? And it said decay to half of the original amount. So if I say original amount is 1, then half is going to be 1/2, right? So if I say original is 1, then decayed half will be 1/2, right? So using that, it will be, again, a equals to a sub 0 times e to the kt exponent. Again, we wanted to find the rate using the example always rate, right? So then we will replace everything else that we know. It will become half from the whole. And K is what we're looking for. And the year is time. T is 5,715. So then this is just same as 1/2 equals to e to the k times 5,750. We don't really need to write 1 down. And when we multiply both sides by natural logarithm, we can bring down the exponents. And natural logarithm e become 1, so we just need to divide both sides by the time t, which is 5,715. That's going to give you your rate. So your rate should be negative this time. Why? Because remember, this is decay, right? And when you do natural logarithm of 1/2 divided by 5,715, you get close to negative 0.00012. And if once you see that negative sign, you kind of know that you got it right once because it was decay, right? So your model will have A equals to A sub 0 times e to the negative 0.00012 t will be your function. With that information, this time, that's the year, right? They found. And that sea scroll contains 76% of carbon-14. So 76% is same as 0.76, right? So you could say when the original amount was 1, what's left over was 0.76. And then time e to the rate. And trying to look for t. And when you multiply both sides by natural logarithm, you end up getting this, where you can divide both sides of equation by your rate to isolate your time. So your t is going to be somewhere close to 2,287. So you could say that age of that sea scroll is 2,287 years old from 1947.